Okay, so the next component that we're going to talk about is the transformer. So we talked about everything that was on the primary side of the transformer, but we're going to talk about this transformer itself. Now, let's just do a little bit of transformer review. Who can tell me basically what a transformer does? Okay, so a transformer, very good, Corey, steps up and steps down AC voltage. We put a certain voltage in, and we're going to get a certain voltage out. Now, if you look at this schematic, now I did not draw the ratios of turns exact as they should be, but when you look at this transformer, can you identify the two components of the transformer, the primary and the secondary? What side is the primary, the left or the right? The left. Very good. How do you know that's the primary, John? Okay, so power comes in the primary, and our new voltages, our transformed voltages, remember, a transformer changes the voltage and current, so it transforms. The name is right in the transformer, what it does. So we're going to have different voltages on the output. Now, looking at this schematic, Andrew, when I look at this schematic, can you tell me if this is a step up or step down transformer by just looking at it? Okay, why do you say it's step down? You're correct. Why do you say that? Very good. There are more windings on the primary than the secondary. So if I have less windings on the secondary, I'm usually stepping down voltage. If I have more windings on the secondary, I'm stepping up voltage. What happens to the current when I step up? Let's say I'm stepping up. Let's say I have 100 windings on the primary and 300 windings on the secondary. My output voltage should go up by a factor of, say it louder, 3. It should go up by 3. If I have 3 times as many windings, I'm going to get out 3 times as much voltage. What happens to my current, John? I'm going to get 3 times less current. That's the most available, depending on the size of the wire and loss and everything else. But in a perfect world, we could get if we triple my voltage, I should divide my current by 3, because we can't step up voltage and current. If we did that, we'd solve all the world's energy problems, wouldn't we? Transformer would be getting out more power than we're putting in. We can't create power that easily. So essentially, this is a step-down transformer. We're going to get less voltages on the secondary. Now, last year when we learned about transformers, we just showed you a primary and a secondary. This particular transformer, though, has multiple secondaries, and you can wind more than one secondary on the same core, assuming it was designed to do that and there's enough room. In the old days, we used to call an additional winding a tertiary winding, meaning third. But in this case, we're just calling them multiple secondaries. So we have our primary 120 volts coming in, and we have 3 secondary windings that are stepped down. Like I said, I just used the schematic symbol that was in the drawing program, so these ratios are not correct. But let's just say that this side here, this first secondary up top, is approximately 5 volts AC RMS. So if I was to put a digital multimeter here, I would read my stepped down AC voltage of approximately 5 volts. The first component that I encounter in this path is just a simple 1 ohm resistor, probably a 1/4 watt or a 1/2 watt, not very big. This is another fusible resistor. So whatever this power supply is feeding, it looks like we have a 5 volt source here because I'm putting plus 5 volts. Whatever this transformer is feeding, if it was to short out, this little resistor might open up because it wouldn't draw enough current to blow the main fuse all the way back here. So this little resistor would open up from too much current. The next component that we encounter is what? D10, a diode. Now, this diode has a particular job in this power supply. Does anybody know what this diode is supposed to do? Moses? Okay, so you're saying direct current. This particular diode is called a rectifier diode. And a rectifier diode's job is to change AC into DC. The job of a rectifier diode is to change AC into DC. If you were to look the word rectify up in the dictionary, it would say to correct or fix. Well, that's our problem. We have AC, but we want DC. And it's rectifying that voltage. So we call it a rectifier diode. You know, I have a problem. We need to rectify the situation. That would be correct or fix, right? Well, our situation is we have AC voltage, but we need DC voltage. So they named this guy a rectifier diode. So a rectifier diode, simply put, changes AC into DC. Now, what does it look like if we were to look at this voltage? Well, if I put a scope back on my secondary, what would I see? Jeremy? I would see a sine wave. Very good. And I'd still see a sine wave right on the back side of this diode, right? What if I move my scope probe over here? Somebody said it. I heard somebody say it. Okay, a flat line. Well, let's pretend that this capacitor is not hooked up. We know that DC, if we were to look at a battery on a scope, we see a flat line at whatever voltage level it's at. But simply right after the rectifier diode, assuming there's no other components in the circuit, will I see a flat line? Okay, so Jeremy's saying it's not smoothed out yet. That's a good term to describe it. So let's jump to this first picture that I have here. We have a transformer and a single diode. And like Jeremy said, on the input side, we would see a sine wave. That's what this blue one here is on the left. Now, current is going to conduct in this direction, allowing the positive cycle of my alternating current to go through the diode. So what we'll see is what we have over here. They're labeling it the resultant output waveform. So essentially, we're going to see the positive pulses of my half-wave power supply. Ooh, I just used a term. Hang on for 2 seconds, Courtney. Half-wave power supply. Why do you think we call it a half-wave power supply? Because the output is half of the sine wave. We're seeing the top half of the sine wave. So the output at this diode is just the top half of the wave. So when the top half of the wave is coming through, the diode conducts. When it changes direction and goes negative, the diode is not conducting. It's in the reverse bias direction, not allowing current to conduct. So it blocks the bottom half of the wave. So we only see the output at the top part. Now, this is not pure DC. Pure DC would look like what Jeremy said, a flat line on the scope. We would see a flat line at the level that my voltage is. But this is just pulsing on and off. So we actually call this pulsating DC. We call this pulsating DC. So on the back side of the diagram, we see our AC waveform. On the output side of this diagram of this diode, we see our pulsating DC output. Additionally, we have a resistor and a capacitor. Now, in this case, this capacitor on the first pulse is going to charge up. And all the subsequent incoming pulses are going to charge this capacitor up. So we're no longer going to see our pulsating DC. During the off time that our rectifier is blocking, that cap is going to be charged up and supplying current. Now, there's no cap drawn here, so right now I have pulsating DC. Let's go to the next diagram where we add the capacitor. So we added the, oh, wow, somebody said smoothing earlier. There we go, smoothing capacitor. The proper term is a filter capacitor. It filters our pulsating DC and smooths it out. Some people do call it a smoothing capacitor. That cap will charge as the incoming pulse comes up. And then as that top of that sine wave starts to collapse and then go negative, the capacitor will supply the energy that's stored. Now, of course, the load will start to discharge that cap, but that's okay because the next incoming cycle is going to charge it back up again. So if we were to look at this on the scope, this is what we would actually see when that cap is there. Now, this is called ripple voltage. Ripple voltage. So we had AC, then we turned it into direct current. We turned it into DC. Then we added our filter or our smoothing capacitor, and that resulted in ripple voltage. So now my voltage might be fluctuating between, let's say, 5 and 5.2 volts. So up here's 5.2 volts. Maybe it drops about 200 millivolts. The next cycle comes in, charges the cap back up. Then it drops a couple of hundred millivolts more. It all depends on the load, how much current is being drawn by whatever this power supply is powering. That gives us ripple voltage. Now let's jump back to our main diagram. Now this power supply I made as simple as possible. There's no other components after it. You're going to see the next two diagrams. I have a few extra components here. And these components provide what we call regulation. Regulation is what will give us that nice flat line that we want to see on the scope of a very constant DC source. So this top power supply is unregulated. It just gives us 5 volts, and there's a little bit of ripple on it. The bottom side of this power supply, like the others, would be the negative. I have these going to ground. When I drew this, I did not write that to ground, but this would be our positive and this would be our negative 5 volts. So if we were hooking our scope or our meter up, we'd attach the negative lead here and scope or measure at these points up here on the positive source. Yes.
So that's off.
Where would you see an unregulated supply? Something that doesn't require as steady as a voltage. Maybe just a voltage that's closing a relay or a solenoid, possibly even running a motor. Something that does not require a highly regulated load. Now, everything that we use that's electronic, like computers and laptops and PLCs, they need to be highly regulated. We do not want to see fluctuation. So yeah, a lot of our sources are regulated, but there are plenty of sources. If this was just lighting up a filament for a bulb or a backlight on a display, that doesn't, you're not going to see those fluctuations. Now, don't forget, let's just go back to this picture. How long of a period of time do we have here? When we look at this sine wave, we know that our power supply is plugged into a 120 volt, 60 hertz power supply. So when you look at this on time, and then you look at this off time that the rectifier is blocking the negative cycle, you have quite a bit of time here when you look at it visually. But how much time is there no energy there? Well, if we use our formula to solve for period or time, we know that time equals 1 over F, 1 over frequency. So 1 over 60 hertz would be 16.666 milliseconds. So when you look at this, we're only looking at half of that. We're looking at about 8.3 milliseconds that it's off. And there's a little bit of time in here added to it. I would say that that cap during the off period of time has to store energy for approximately 9 milliseconds. And of course, we want some excess because we don't want it to go totally dead, or this would dip way down. We'd have a sawtooth wave then. It would look like triangles. The bigger the cap, the longer it'll charge it or hold that charge. But it is still a relatively short period of time. Now, of course, electricity travels approximately at the speed of light. So maybe 16 milliseconds seems like an eternity when you compare it to that speed. But nonetheless, it's not a huge amount of time. As quick as that cycle goes off, it's coming back on about 8.5 milliseconds later. So this top power supply we call the half-wave rectifier. It's a half-wave rectifier because we're literally turning off the power supply for 180 of the 360 degrees of our sine wave. Half-wave rectifier. Let's talk about this last component. This component can be on this side of the cap or this side of the cap. Some devices don't even have the component. It's a resistor. It's a pretty high resistance resistor in comparison to our voltage. 2.2 kiloohms is not a lot of, it's not going to draw a lot of current at 5 volts. It's called a bleeder resistor. And what a bleeder resistor does is it discharges the cap when the device is turned off. So any energy stored in the cap will now bleed off to ground through that bleeder resistor. But it also, let's go back to this picture, it also limits how high this peak charge will be. Because as quick as the cap is charging up, the bleeder resistor is starting to discharge it, as well as the load it's supplying. So by adding a bleeder resistor, we actually reduce the ripple by a little bit because it may not make it quite to its peak voltage. Because as quick as it charges up, the bleeder resistor is already starting to discharge it. So instead of maybe making the peak up to here, it only makes it to here, which minimizes our ripple a little bit. So the bleeder resistor does two things. It minimizes ripple and it discharges the capacitors when the power supply is turned off. Discharging the capacitors gives us a margin of technician safety. I mean, if you're a technician and you go inside a device, those caps should be discharged after you turn it off, providing safety for you. Yet, whenever you guys work on a power supply out there, you'll see me, if we have it open, I'll say, well, let's discharge the cap to be sure that it is discharged, because not every power supply has a bleeder resistor, and maybe the bleeder resistor failed, so we don't want to take a chance getting shocked. Okay, that covers the half-wave rectifier. Let's move to the next one. This middle power supply. This transformer secondary looks a little different. Looks pretty close to this one, but I added a little connection here. Somebody said it. Say it louder, please. Okay, this is a center tapped secondary. So this power supply that we're going to cover right now requires a center tapped secondary. Now, I want you to just imagine that this resistor is gone and that this diode is gone and that this diode is gone. Let's pretend we could erase this, and erase this. I zoomed up on it. Let's pretend we're erasing this guy, we're erasing this guy, and we're erasing this guy. Wow, it really looks a lot like the top power supply, doesn't it? We got a rectifier diode, a filter capacitor, a bleeder resistor. We're going to ignore this guy for now. We're going to pretend this isn't here and this isn't here. So it really looks like a half-wave rectifier, doesn't it? But by adding this, doesn't that seem like we just added a second half-wave rectifier? Well, here's the interesting thing. If you took a scope and you measured from the center tap to the top of the transformer, you would see your sine wave. If you used a dual trace scope where you can monitor two sine waves at once, and you set your second channel, your channel 2 or your channel B, to the bottom half. So we're looking at the top half of the sine wave and the bottom half, and we're looking at that sine wave. The sine waves would be 180 degrees out of phase. So when the top half of the transformer is going positive, the bottom half of the transformer is going negative, which means this rectifier will be conducting, drawing that first pulse. This one will be blocking. But when the AC changes direction on the top half, this one will be blocking and this will be conducting. So we're going to get a pulse and then another pulse and then another pulse. So it's going to look a lot different than our half-wave power supply. It's not going to have a long off period of time. The other thing about a center tap transformer is if I was to measure the voltage, and let's say it was 10 volts from the top to the bottom, by adding that center tap from the center to the top would be 5 volts. and from the center to the bottom would be 5 volts. The center tap cuts the voltage in half. Now let's look at that output that I just air drew. Let's go to another diagram and let's look at this guy. So here is another drawing of our power supply. But see, remember how I said, okay, the top diode will conduct, and that'll give me my first top half of the sine wave. When this one is blocking, when it changes direction and blocks, this one will be conducting. So what happens is we end up with a pulse, and then another pulse, and then another pulse. Instead of our half wave, which was on and off, and on and off. This is on, and then as soon as it hits 0, it goes on again. So we're getting twice as many pulses per second. When you look at this one, there's your on and a really long off time. When we go back to this one, it's on, it's on, it's on, resulting in twice as many pulses per second. This particular power supply, these diodes are taking turns. I wish we could slow the AC down and make each diode light up. You'd see this one light up, then this one light up, then this one light up, and then this one light up. If this was LEDs, you would actually see these diodes alternating as it takes turns. Of course, 60 hertz, it's happening, in 16.666 milliseconds on the primary. We couldn't see that. It would look like the lights were on constantly. But here's the thing. If previously our frequency was 16.66 milliseconds, what do you think the output of this is? If I have twice as many pulses per second, doesn't that mean the time was cut in half? So the output of this rectifier scheme is 8.33 milliseconds at 120 hertz. So 60 hertz comes in, but my pulsating DC frequency is 120 hertz. This one, 60 hertz came in and 60 hertz came out. Why? Because one cycle, we still get 1 pulse per cycle. This one, we're getting 2 pulses per cycle. So that's 120 hertz is the output. What is this power supply called? Well, because we have voltage 360 degrees, it's a full wave rectifier. Also called the full wave center tap rectifier. So sometimes they call it a center tap, sometimes they call it a full wave. Now, I know you've all learned the schematic symbol for a full wave bridge. Don't confuse this with a full wave bridge. It's similar but different. We're going to go over that next. So this is a full wave center tap rectifier, or just simply called a full wave rectifier. Same deal when I add a capacitor. When I add a capacitor, it's going to smooth it out, but this sawtooth wave will be 120 hertz instead of 60 hertz. So here's my filter capacitor here. Here's my bleeder resistor here. Interestingly enough, I picked these values when I drew this schematic on purpose. A half-wave rectifier generally requires a larger filter capacitor or smoothing capacitor because it has to store energy for a longer off period of time. You can usually get away with a slightly smaller filter capacitor because the off time on a full wave power supply is much less. Again, if we look at this off time, we only have to store energy during this period of time. When you look at that half wave power supply, you're storing energy this big period of time that it's off. So the advantage of a full wave rectifier is that we can use a smaller capacitor. But it does require 2 diodes instead of 1 and a more complicated center tap transformer, all adding cost to our device. And maybe even a little bit of size. So, there's always advantages and disadvantages to things. A half-wave rectifier is probably the simplest power supply. So that's the advantage. This guy requires a diode and a secondary, a filter capacitor that might be a little bigger and a bleeder resistor. So it's cheap to build. It's simple to troubleshoot. There's not a lot of parts. You know, probably takes up a little tiny bit less space again because there's less parts. When you get to the full wave center tap, there's twice as many diodes. It requires a center tap transformer, but it is more efficient. It's more efficient because we're using the entire wave. It will have slightly better voltage stability, meaning regulation. It's easier to smooth or filter out the pulsating DC because the off period of time is much shorter. So it is a better power supply, but it does cost a little more to build. So that was our full wave center tap or our full wave rectifier. Now let's scroll down to this guy. Oh, let's hold off on D4 for the moment. That's a regulator diode. We're going to talk about that a little bit later. Now our bottom power supply. I already gave you a hint as to what it was because you had to memorize the schematic symbol way back when. This is our full wave bridge rectifier. The output of our full wave bridge rectifier looks very similar to our full wave center tap. It's 120 hertz consecutive pulsating DC. But the difference is it does not utilize a center tap transformer. So the center tap transformer, the disadvantage of that is it cuts the voltage in half. So only half the available voltage is there. But by adding these two diodes, it gives me a path to ground on one cycle and then the next cycle. And what that does, it allows me to utilize all of the transformer voltage. So let's say that this was 12 volts RMS. I'm not dividing it in half like I did with the center tap. So now I'm getting all of my transformer voltage. So the output of a full wave bridge rectifier is going to be a higher voltage than a full wave center tap rectifier, assuming we had the same amount of windings on the transformer. Again, it converts AC to DC. We end up with our 120 hertz output. There's our ripple up top. But the main difference is those two additional diodes let us not use a center tap transformer, and we get twice the voltage out. So the bridge rectifier's advantages, we're utilizing the entire secondary voltage. I guess the disadvantage would be there's a couple of extra parts. Again, you know, we got two more diodes. You know, whether it's a big piece of industrial equipment, medical equipment, defense industry equipment, or something simple like your cheap piece of consumer electronics. You know, if I add 2 or 3 pennies to the manufacturer cost of all your devices, and the manufacturer, you know, let's say it's, Dell or HP, and they're making computers, you know, and I got to put 2 more diodes in there at a cost of 3 cents. If I'm making 1 million computers a year, that's a $30,000 savings. So everywhere they can save a penny or two, they will if they can get away with it. So it's like, oh, what's 2 diodes? Doesn't seem like a big deal, does it? But to them, it adds up in the end. So the output of this rectifier would be 120 hertz, just like the full wave center tap, but the voltage will be twice as high. Again, we have a smoothing capacitor and a bleeder resistor. Now let's talk about what's after those components. Well, this first one here for my full wave center tap power supply, I have, it says D4, 5.1 volt, and it's a Zener diode. Can anybody tell me how a Zener diode is different than just a conventional silicon diode? What was different about a Zener diode? And it has to do with this voltage rating that I put next to it. Does anybody remember that from 11th grade? Okay, sometimes they call them Avalanche Diodes. So essentially, we know that a diode simply allows current to flow in one direction and blocks it in the other. But what an Avalanche or a Zener diode does is it has an avalanche voltage rating. And this one happens to be 5.1 volts. So let's say I put my meter across this filter cap. And I'm looking at my ripple voltage. And my ripple voltage is right here. And let's say that this dip is 5.2 volts, and this peak is 5.5 volts. That's above the avalanche voltage of 5.1 volts. Anything that's above 5.1 volts will now pass backwards through the diode and get bypassed to ground. This is called a shunt, S-H-U-N-T, a shunt style regulator. I shunt or bypass any excess voltage above the avalanche rating to ground. Now, most Zener diodes would have a resistor in front of it to limit how much current could flow through it so you don't damage the diode. But nonetheless, the job of this is to take anything that's over 5.1 volts and bypass it to ground. And it would normally be dissipated in the form of heat. It's not a very efficient regulator. We're basically taking our excess energy and sending it to ground and getting rid of it and dissipating it in the form of heat. There's a limited range we can regulate with a Zener diode like this. It's probably the simplest regulator there is. Now, this next one is called a linear regulator. It looks like a three-legged transistor that mounts on a heatsink. And it's probably the most common regulator used in industry. We call it the 78 series regulator. The 78 series regulator is usually followed by 2 digits telling you how many volts there are or that it regulates at. So usually I can put 10, 20, 30% higher into my 7812 regulator here, and it's going to give me 12 volts out. So let's say that the output across this capacitor with the ripple voltage is between 16 and 15 volts. All that excess voltage is going to be bled off the ground because this is still a shunt regulator, but it's designed differently to be able to carry more current. And it's going to give me a very stable 12 volts out, giving us, again, that proverbial flat line on the O-scope. The 78 means it's a positive going regulator. If you see a 79 series regulator, it means it was designed for negative voltage. We have 7803, 7805, 7808s, 09s, 12s, 15s, 18s. I think they go up to about 50 volts. So the last two numbers is the voltage that it's designed to regulate at. And the first two numbers mean it's either a positive or a negative going regulator. So if I had a negative power supply, it would be a 7912. Lastly, this 18-volt Zener diode, you look at that and think, well, it's across the output like this one, so it must be a shunt regulator. But if my voltage is only 12 volts, what is this guy doing right now? It's not doing anything. It's not avalanching. It's just sitting there blocking. So it's not really doing anything. But it will do something when one situation occurs, whenever my voltage shoots above 18 volts. But wait a second. How can my voltage shoot up beyond 18 volts when I got a 12-volt regulator there? If that regulator fails, maybe a power surge. So that voltage shoots up and this clamps down on it, sometimes shorting out, but protecting whatever this 12-volt power supply is powering. Maybe it's our very expensive control logic circuit for, that $1 million MRI machine at the hospital. Or maybe it's just that, $300 Intel processor you just bought for your super fast computer. Nonetheless, it's surge protection. So while they look exactly the same, when you look at the voltage rating, if the voltage rating of the diode is the same as the output of the power supply, that would be a regulator. If the voltage rating of the Zener diode is higher than the regulated output of the power supply, then it would be for surge protection, to clamp down on voltage that goes above that limit. Okay, a minute ago, I said 7912 would be a negative power supply. So we didn't really talk about that here. Let's go back to our top power supply. How would I make this put out negative voltage? Here's our half-wave rectifier, and it's putting out positive 5 volts. What could I do to make this power supply put out a negative 5 volts? Wow, everybody's hand went up. Andrew,
You would reverse the diodes.
Okay, so D10, we would flip in the opposite direction. And then D10 will allow the negative side of the sine wave to come out. Now, what you don't see here is that this is a polarized electrolytic capacitor with a plus and a minus. Would I have to change direction for that? Absolutely, because we know that if we put an electrolytic capacitor in backwards, we're going to get one of them nice little pops and booms, and the magic smoke will come out, and our device will no longer work. I've done it myself once or twice too, my friend. We all, even the best of us, mess up. Same thing for all these. If I was to flip D2 and D3, we would have a negative output, which means I would have to flip the direction of C2 as well as D4 here, wouldn't I? Because everything's backwards. And the same deal here. D5, 6, 7, and 8 would have to be in the opposite direction. C3, the minus would be up top and the positive would go to the ground. And this would not be a 7812. This would be a 7912 regulator.
Basically, everything that's directional gets flipped.
Our semiconductor devices and our electrolytic capacitors, yes. Anything that has polarity is going to have to be flipped. Okay, so what we're going to do next is we're going to breadboard these power supplies and then measure and scope the outputs and see if everything that I said is true.